to think of the following, that the knot diagram itself is sitting inside the surface, right? And you can think of it as having 3 nodes and as many edges as there are in the diagram. So how many edges do we have? You have 4 times the number of nodes. V could be equal to the number of crossings in the diagram. Four times that is twice the number of edges in the diagram. So twice the number of crossings is equal to the number of edges. So we know the number of crossings, we know the number of edges. And then there are the 2 cells. And there is one 2 cell for each Cipher circuit. So that tells us that vertices minus edges plus, and let's let S equal to the number of Cipher circuits. So then I have vertices minus edges plus the number of 2 cells, 1 cells, 0 cells, 2 cells, is equal to 2 minus twice the genus by Euler's formula. And so we had that E is 2V, so this says minus V plus S is equal to 2 minus 2G, but I forgot something. I forgot that I didn't close off the last thing, the boundary. So really I need plus 1 in order to think of a closed surface with a given genus. All right, but I'm forming a surface with boundary, but let's assume it has 1 boundary. If it's a link, then there would be more than 1 boundary, and this would be L, where L is the number of link components. Because for each link component, I have to close it off to get a closed surface to count genus. So we're going to let L be equal to the number of components of the link. All right, so now I have that, and that tells me that 2G is equal to V minus S plus L minus 2, if I'm not mistaken, which I probably am. Let me see. Plus 2, right? V minus S plus L, no, minus L. Just doing the elementary algebra here. Minus L, right. V minus S plus L equals minus 2 plus 2G. So then the 2 comes over here, and we have that the genus is equal to V minus S minus L over 2 plus 1. And we'll see whether that worked out by doing it in our case, where I know this is a torus. So in this case, what did we get? We got that the vertices is equal to 3, and the Cipher circuits is equal to 2, and the L is equal to 1, and we get 3 minus S minus L over 2 plus 1 which is exactly equal to 1. So it looks like I'm in the right ballpark there for the genus of the cipher spanning surface. Now, this is the usual way of thinking about that surface. And I want to talk now about a way to think about it in terms of cobordism. But before we do that, I think I should mention to you a couple of facts about this surface other than calculating its genus. A nice exercise for you, that it always gives you an orientable surface. Let's look again at another version of it for the trefoil knot. That will underscore this point. Now I've drawn it in such a way that the two disks are very apparent. All right, here's one of the disks. And here's the other disk. And as you see, that if you started here, then your normal vector will get flipped when you go through the twist, but then you come back and you see that any path that takes you between these two has an even number of flips. And so indeed, it's apparent that this is an orientable surface. Some surfaces spanning the link are not orientable. And may be interesting to study. For example, consider the trefoil knot again. And consider this surface. The boundary of F is equal to the trefoil knot, but F is equivalent to a Mobius band. It's not orientable. And in generally, a choice of checkerboard surface may or may not be orientable. So that's why, you see, what I'm saying is, you see, what I'm saying is, you could start with an arbitrary knot diagram or link diagram. And then you could choose a checkerboard surface if you wanted to. Fill it in so that it's two-colored as a graph. And of course, you are now looking at a surface whose boundary is the knot by putting in twists between these disks that I've indicated. But is this orientable or not orientable? Well, you can do some pathways in here and check. It might have been orientable. I didn't try to make it orientable, but I could start somewhere like here, and then see whether there's an odd path going through an odd number of crossings to get me back. 1, 2, 3, 4, 5, right there. So it's not orientable. Let's see if I got that right. 1, 2, 3, 4, 5, and return. So this is not orientable. But of course, sometimes there are checkerboard surfaces that are orientable, and that's a nice puzzle to think about. So I offer that to you as something interesting to think about, and we'll go on, because I want to show you this cobordism way of thinking about producing surfaces for a classical knot, which will let me do something similar for a virtual knot. You see, if you have a virtual knot, let's face it first of all. Well, no, let's just talk about the cobordism method. So I'm going to go back to the trefoil again. And I'm going to prove to you that I can do a cobordism. So there's an obvious way to do a cobordism on any knot. You go up to each crossing and you see that one way to look at the crossings in the knot is that there are 2 inputs and 2 outputs. But if you go along the side of that, then you will see something like this. And then you will notice that is a candidate for doing a saddle point, right? Goes in, goes out. You can do a saddle right there. Can do saddle. So that means that I have a potential saddle that I can do here, here, and here. So let's do all those saddles, and that gives me a cobordism to another situation. So let's see what that looks like when I do it. So there's a cobordism here. But now, you see, from the point of view of cobordism, this is equivalent to, you can undo the curls. And then this can be taken by death to nothing. And so the whole result is that I started with the knot K, and I did 3 saddles. But now let's be careful, because I ran out of room here, so we better be particularly careful. Think of doing them one at a time so that you can keep track of what kind of genus you're producing. So on this slide, I will go one at a time, and then, let's back up there. Just going to do one saddle at a time, so. All right, that's doing one saddle. Yeah? One saddle. And now I have two components. And then what was my next saddle? That was right here. Right here. And I ended up here. And now I'm down to one component again. And I see this is, I really should use more room so that you can see what happened here. Let's go to another slide and really do this carefully. We'll get rid of this. Now, we said that we could do one here, we could do one here, and we could do one here, and we're going to do them one at a time so we can see what happened. Oh, really not. My artistry is failing here a little bit. Too thick, the lines are too thick, but we'll work with it that way. Yeah. The main point being that on the first try, I went to 2 circles, yeah. And then let's do it again. That's with 2. And with 2, you see I'm down to 1 circle. But I really went 3, right? And on 3, I split back another circle. So you see, it isn't the most necessarily the most efficient sort of thing, but it's a very systematic thing that I can do. I can do one of those operations at every crossing. And I think you understand that what I'm getting at is that if I do that, I produce what amount to the cipher circles, but they are being interpreted as parts of a cobordism instead of just a construction for a surface, right? And let's draw a schema of this cobordism. So we started with this, and on the first step, we split into 2 circles. The knot, and then A and B. Then I did this, which is a saddle point between the two circles. So I went back to one circle here. And then it was redundant, but I did it. I did another saddle, and I ended up with the two ciphered circles in this fashion. And then these are both trivial. They both bound disks. And so I bounded them both with disks. And I end up with this surface F. And this surface F is contained in S3 cross I in the following sense. Here is S3, and here is the knot, and here is S3 cross I walking along like this. But what we did was we formed a surface. Well, let's just draw it this way so it looks like an honest circle here. And then it went through a saddle point, and then it died off like that. And it formed, and we formed a bit of genus in the middle. And so we have this surface F, which is sitting inside of S3 cross I. It's not inside the 3-sphere anymore. But the genus of F, I leave it to you, exercise this now. One, the genus of this surface F is equal to the genus of the ciphered surface. Now that's not going to be hard to show because the combinatorics are almost identical with the ciphered surface. And secondly, in fact, F is equal to the result of pushing the ciphered surface into S3 cross I. And by pushing, I mean that you have this surface which is sitting in 3 space, and you can push it in the 4-dimensional direction so that it's a nicely embedded surface in the 4 space, keeping the boundary in the 3 space. But the beauty of this construction is the following: that it can always be done for virtual knots. This cobordism construction can always be done for virtuals. Let's look at an example. Here's a virtual knot, and you immediately see my problem in trying to do the usual construction here because of the virtual crossing. I don't have a way of creating a surface in 3 space from the knot diagram with the virtual crossing, not directly. But I can, if I want to, go through a cobordism, and I'm going to go through a cobordism by using this and by using this, just like we did before. So we're going to, let's do it in 2 stages so we can see what the genus is and everything. We go once, and go through that saddle. And then we're going to go one more time. and go through the other saddle. And now this is our ciphered circuit. And in this case, there's only one ciphered circuit, S. Okay? And the number of, so S is equal to 1 in the end. You smooth them both out, just like forming ciphered circuits. Don't do anything to that. The number of crossings is 2. Number of classical crossings is 2. And the number of components is 1. And if we used our formula, it would say the genus of the resulting surface should be equal to V minus S minus L divided by 2 plus 1, which is going to be equal to 2 minus 1 divided by 2 plus 1, which is equal to 1. So the claim is that we're getting genus 1 again, and let's do it by checking it one at a time. What happened was we started with the curve, the knot. We went through one saddle into two curves. Then we went through one more saddle that brought us back to a single curve. And that single curve is, notice, the single curve is equivalent to this, which is equivalent virtually to this, and this can go by a depth. Right. So it caps off. And the genus is equal to 1, as predicted by our formula. So you see, the ciphered construction can be reinterpreted as a cobordism, and then we have the result. We have the result. That if K is a virtual diagram with V nodes, V classical nodes, and L components, then K is equal to the boundary of S of F, genus of F equal to V minus S minus L over 2 plus 1, where F is a cobordism surface for K, obtained by virtual moves saddles, births and deaths. So we say K equals the boundary of F. F is contained in virtual force space. So every virtual knot bounds the surface of some genus in virtual force space. Now we can state our question, which is, given K, what is the least genus G for an F, boundary of F equal to K, F contained in virtual force space. And when I say a surface is in virtual force space, I mean it's the surface that is described by doing saddles and births and deaths like this. So this is the corresponding problem for virtual knots that is a very hard problem in general for classical knots. Now let's go to the slideshow and see some of these phenomena at a little more rapid pace. So, as I'll be repeating myself a little bit. Here's virtual cobordism. You're familiar with it. Here's a nice example. And I can't recall whether we did this example before, but it doesn't hurt to look at it again. It's a very interesting example. So this is an example of a virtual knot here. I call it the virtual Stevedore because the classical Stevedore knot has a crossing here and a crossing here. So I've made it into, I've converted the Stevedore into a virtual knot with fewer crossings. This only has 4 crossings. And then I do a virtual move to make a saddle point move available right there. And then I go through my saddle. And now I notice that I have a consecutive sequence of virtual crossings here. So I can do a detour move and get it over to here. And then you see it's unlinked. And so these can both die. So the story for the surface we just produced is that we went through a saddle, we got 2 components, they moved apart and died. So this is a surface of genus 0. So this fellow here bounds a surface of genus 0. If you were to use my Cipher method on this, you would find that it bounded the surface of genus 1. But we can do better than the Cipher method in this case and find out that it is slice. We say that a knot, virtual or classical, is slice if it bounds in force space a surface of genus 0. So this is the phenomenon of sliceness. We're about to see that if you take the connected sum of a knot and its mirror image, it's always slice. But then there are examples like this guy here, which are not connected sums with a mirror image or connected sums at all, but are nevertheless slice. And so the question is, can we classify slice knots? This is just another picture of the virtual Stevedore. I won't bother you with it. This, however, is of interest. I wish to prove that the virtual Stevedore is not classical. Down here at the bottom, you see a realization of our virtual Stevedore on the surface of a torus. Remember that we can realize virtual knots on a surface, and here it is realized on the surface of the torus. And now I'm going to work hard, but you can stare at the slide. I'll give it to you. I'm not going to work hard here. I'm just going to point at it. I can expand the bracket for the, notice these are the virtual crossings here and here. I can expand the bracket into all, well, let's see, we have 4 crossings, so there's 16 states, and here they are, all A's, all B's, and somewhere in between. And you can look at the curves that you get on the surface of the torus. And then you can argue that there couldn't possibly be a homeomorphism of the torus that throws this knot into a genus 0 subpiece of the torus, because the curves couldn't be thrown that way. And you have to look carefully at the isotopy classes of these curves on the torus to see that. I leave that to you, but that's what I call the surface bracket polynomial, where you expand the states and then you examine the isotopy classes of the state curves to make deductions. So it isn't a classical knot. That's good to know. Yeah, and so our example is a complete one in that sense. Here's another example. I want to show you what happens with mirror images. So here's a knot K, and here's its mirror image. Now I have taken its mirror image in a plane, and I've reversed its orientation so we could do a saddle between these two and make a connected sum. And so this is the connected sum of K and its mirror image. And it's the connected sum of K and its mirror image that's going to turn out to be slice. And here is a picture of that happening. I go through this saddle point. Then I look at it and I decided what did I decide to do? I decided to go through one more saddle point right there. See, this goes down, that goes up. I go through one more saddle point. So I went through two saddle points. Now I've got a lot of components because that's with respect to one component in itself. So I have one extra component, now I have another extra component, and now I examine it carefully and see that it's pulling apart and becoming a trivial link. And you have to watch carefully because you see this goes across by a two move, comes out, and so on. But the three components are all separate from one another, and they all die. And so we went through two saddles, and no production of any genus, and it's all gone. And this pattern works in general to show you that the connected sum of a vertical mirror image with a knot is slice. I'll let you think about that. I'm repeating my definitions here. K is concordant if there is a genus 0 cobordism, and it's slice if it's concordant to the unknown. And here's this story I told you about the spanning surfaces. Classical Cipher surface, cobordism Cipher surface, cobordism Cipher surface in the case of this. And let's see, I used R for the number of cycled circles and N for the number of crossings. And maybe I made a mistake when I was doing my derivation before. Let's see. In the case of L equals, no, I didn't. You'll notice that if L equals 1, then you add minus L, all divided by 2, plus 1, but you can put it all over 2, and then it's 2 minus 1 is 1. So this is the correct formula in the case of one component. All right. And this is a picture as I was showing you before. Now I want to tell you about a theorem, but we won't prove this theorem now, but we will prove this after we do Carvanothomology. Next week we're going to start Carvanothomology, or maybe even a little bit now, but I think we don't have time to do it now. We'll start Carvanothomology next week. If we have a knot diagram, okay, then the formula for the genus of the Cipher surface, the cobordism Cipher surface, is minus S plus V plus 1 over 2, from what I said before. R is S, N is the number of nodes. The theorem is that the four-ball genus of a positive virtual knot, all the crossings are positive, is given by the Cipher cobordism surface. That's as small as it can get. Isn't that amazing? That's the theorem. And the proof is not so easy, but it is easier for us than it was than the corresponding proof was for the people who invented it for Carvanothomology by way of the first time. Because, you see, there is a Carvanothomology theory for classical knots and an invariant due to Rasmussen, which enabled one to prove the corresponding theorem for classical knots. And it turns out that one can generalize these things and make them work for virtual knots. And you still have to do some work, but of course it isn't as highly original as the original approach. And the original approach was able to prove this theorem, same theorem, Cipher genus, for the case of classical knots. And Heather Dye and Aaron Castor and myself managed to generalize this result to virtual knots that are positive in this way. So that's on our docket to talk about. Now, these notes start talking about the ARF invariant, but I'm going to skip this. I'll come back to it. The ARF invariant is the classical invariant of knots, and it's related to the following switching move that you can do on the diagrams. Oppositely oriented lines, switch all four. Classically, it turns out that if you're allowing yourself to do that, you can only get two classes for your knots, the trefoil and the unknot. And then that class is a concordance class for knots. Very interesting. And then I would like to understand it better for virtual knots. And I'll come back to this, but I'm not going to do it now because I wanted to talk about the affine index polynomial, which we had talked about before. So I'll skip this part of this slideshow and remind you about the affine index polynomial, which we started talking about 2 weeks ago. And I want to show you that this affine index polynomial is a concordance invariant. So it lets you check whether some knots are concordant to others or not. So you may or may not remember this invariant. Let me recall it for you again. If in a flat version of the knot diagram, here's the knot diagram, here's a flattened version of it, you look at the way the oriented curves pass by one another and you form a labeling of the arcs in the diagram, of the edges in this graph. If this edge has label B and you cross, and the line you cross is going to the right, then you increment the B. If this label is A and you cross, you decrement the B if it's going to the left. Going to the left, down, going to the right, up. Here's the labeled diagram. You see, 0 went to the left, minus, went to the right, 0. 0 goes through the virtual crossing without any change, goes to the right, up 1. 1 goes to the right, up 2, up to 2, goes to the left, down 1 to 1, goes to the left, down to 0, and we're back where we started. There's the labeling. You can always do this. The labeling will always work out. Once you have the labeling, you form weights. Now, I'll give you the rule, and then we'll discuss what's going on here. The rule is that you go up to the crossing, and there are going to be two weights. One is across the input to output line without going through, or across the input to output line but not going through, like the two sides of the cipher smoothing. For plus, it's the top difference, A minus B minus 1. And for minus, it's the bottom difference, B minus A plus 1. They are negatives of one another. So let me do it here. I've written W minus and W plus. So at A, the W minus is 1 minus minus 1. This minus that. Going in, going out, along the lower edge. That's a minus 2. On the upside, 0 minus 2. I see. There's a misprint on my slide. This should be W plus, and this should be W minus. These are switched. Can you handle that? This is W plus and that's W minus. So the W plus is the one on top. 0 minus 2 is minus 2. 1 minus minus 1 is plus 2. Let's go to B. 2 minus 0 is 2. Minus 1 is minus 2. And over here at C, 1 minus 1 is 0 and 0 is 0. Okay, so then for K, which has all positive crossings, we use the plus signs. Those are the ones in the left column. And so we get, and the definition of the polynomial is, I didn't write the definition of the polynomial, but I wrote it last time for you. Let me write it on my slide record so you understand it again. So the pk is equal to the sum over the crossings of the sign of the crossing times t to the weight of the crossing minus the writhe of the diagram. Now, the weight of the crossing is equal to the W of sub sign of that crossing. So it's W plus if it's a positive crossing and W minus if it's a negative crossing. So that's the definition of the polynomial. And this is invariant under the virtual moves. And I remember now, you should all be experts in this because we spent quite a lot of time doing various things about this invariant, remember? But I just wanted to recall that. So here we are, and then here's a simple example. You would see that if you take the connected sum of K in a mirror image, it'll come out 0 because everything over here cancels everything over there. Well, there's our definition. I won't worry you about it further. It is interesting to do this, however. This is for flat diagrams, diagrams that have not over nor under for the crossings, the classical crossings. They still are not allowed to detour over the virtual crossings. So we have the flat crossings and the flat index polynomial, and it's defined in the following way. I take the absolute value of the weight, but it's still integral. And then I get a polynomial, and I regard its coefficients modulo 2. So once I regard the coefficients modulo 2, there are no signs of crossings. So all you have is t to the absolute value of the weight of the crossing plus 1, which gives you the effective writhe compensation. And this is an invariant of flats, and it's an invariant of concordance as well for flats. So we need an example or two. Here is a couple of calculations where in one case I have a non-trivial one, and in the other case I have a trivial one, but we're edging towards the end of our time, so I'm not going to go through that calculation. I do want to point out what happens if you try to label a link. It's interesting. Notice what happens here. You try labeling this link, and this goes down by 1, but it comes back around and has to be equal to itself. So it can't be. A minus 1 is not equal to A. So that some links can't be labeled. On the other hand, this can be labeled. You start with B, you go through, it's B plus 1, then you come back, B. And similarly here, this has to do with the fact that it's classical and that what goes up must come down because you go through an even number of times. And you can define the index polynomial for links that have labelings. This is quite interesting and worth looking at for a moment. Here's a hop link, and I've tried to label it. I labeled starting with a P label here and a Q label here. And then P goes up by 1, and then it goes back down. And Q goes down by 1 and back up. And if now I'm looking at the weights. And you see that when I look at the weights, like here, Here, I'm going to be looking at Q minus P minus 1. So the difference between Q and P becomes important in the weights. All the weights are expressed in terms of these differences. And I could say that my polynomial is given by t to the minus n plus minus 1, t to the n plus 1 minus 2, where n is that difference. It's only the difference that makes sense. And so I can think of this as an extra variable. And then I have a polynomial for links. In this case, it's detecting the classical linking of that. And here's a virtual link. And again, I get differences, and I get a polynomial for it. And you can go on into other examples, like here is the virtual Borromean rings. It's a little like the Borromean rings. It's certainly the case that if I drop any one of the components, the other two fall apart. And I can go through the labeling process and find the differences and get a polynomial for that and detect its non-triviality. That's one thing, and an interesting thing to explore. I won't go on with that. But now I want to show you the interesting thing, that concordances will not change this polynomial. And the reason is that concordances are composed of relatively elementary concordances. Let's look at this example here. Here is a nice, big, complicated virtual link. And I go through this saddle. And I went through this saddle. And then once I've gone through this saddle, I see that hanging on this component, which is non-trivial, is another component which actually is trivial. You see, it pulls out and unturns and pulls off. There's nothing going on with it. It's just gone. And so this complex thing is concordant to this simpler thing. And I want to argue that they have the same index polynomial. And you can see the beginning of what the argument is going to be like. Because if I could just get the colors to be the same here, then I would have colors here, which became colors here under the cobordism. And then everything about this would have its own labelings and everything. And the Randomizer moves wouldn't change the polynomial as it moved around and slipped off and didn't affect anything. And so that's the idea, that you need to match the colorings at the points, at the saddle points, and then let it break up into simpler things that don't contribute, that end up contributing nothing. So if you were to look at this, you would see how this part ended up contributing nothing. And of course, you have to think about what happens under some slightly more complicated kind of elementary thing that goes on in your concordance, like this one, where there's a birth that happens, and then it goes through a saddle point, and then there's a death, and this continues on. And you can verify that the sum of the polynomials of pk and pk prime is equal to 0. That's because they bound down in here. And the sum of pk and pk double prime is equal to 0 here. And then it follows that the pk is equal to the pk double prime by doing work similar to what I'm sketching. And in general, a concordance between two things looks like this. So you will see a lot of these basic elementary exchange is happening, births, saddles, cancellations. So that's a sketch of the fact that PK and the flattened one are concordance invariants. I'm looking for an example or two to show you. This is an example that's being worked for various reasons, but we won't. Let's look at this example. So the basic example is K plus over here. And K plus has all positive crossings. So according to the theorem I quoted you of myself and Heather Dye and Aaron Kastner, the genus of this will be the genus of its Cipher cobordism surface, which we could figure out. And on the other hand, I'm interested in the affine index polynomial for this. And then I'm also interested in what would happen if I switch one crossing, which is what I've done here. So we can calculate both of these from the weights table. Let's look carefully. It's been labeled, and let's just check the weights. At A, 0, yeah. At B, 0 minus 1 is minus 1, and 0 minus minus 1 is 1. At C, minus 1 minus 0 is minus 1, and minus 1 minus 2 is 1. And at D, we have 1 minus minus 1 is 2, and minus 2. So there's the weights. Now, if we want to calculate the polynomial for this one, everybody's positive, so we have T inverse, that's 2T inverse, and 2 and T squared. And the writhe is minus 3. So that's the answer. Now, if we switch this crossing, then this one is negative. That's B. B becomes negative, and so we're going to have minus T. It looks like I made a mistake. Let's get it straight, get it correct. The A contributes nothing. The B is going to be made negative, right? So that will be a minus T to the first power. Then the C is positive, and the D is positive. And so that will be a plus T inverse and a plus T squared. So this, it's non-trivial in any case, but there's a sign error here in the slide. All right. There's non-trivial. Being non-trivial, that tells us that it isn't slice, okay? Even though we switched to crossing, it didn't make it slice. So then we can investigate it. See? Here's the one, this is the K, the one with one negative crossing and two positive crossings. So I decided to investigate it to see how close I could get it to be sliced. So I go through a saddle point here. And that gives me a little curl, and I retracted the curl. I did two steps at once. So when you see a crossing, you can smooth the crossing. that takes it through a saddle point. That's the moral of what we had said earlier. And now we have two components. And I'm going to go through another saddle point here, which is between two components. And I'm here. And going through two saddle points, first to break into two components, and then to come back into one component, gives me a genus. That creates genus 1. And now I'm looking at this and I see a detour. What detour do I see? Let's see, go from here through here over to here is the same as going directly over to here, right? From here to here can be accomplished more efficiently than if I went all the way through here to virtual crossings up to there. So we can detour to this. And having detoured to that, we have a Randomizer 2 move that pulls this arc in, and then it goes away. So you see that at that point after the two saddles, I created one genus and could cap off the rest. So this has genus 1, this surface. But now I've proved something because I know, pardon the sign error, that our K has a non-trivial affine index polynomial, and therefore it can't be of genus 0. And therefore, having shown that it's of genus 1, it is of genus 1. And this is going beyond the kind of thing that I could do with the general theorem using Carvanothomology. This is just more elementary, but it lets me prove that this knot here, which isn't positive, actually has genus 1. So there's lots of room for exploration here and trying to understand relationships between genus and the affine index polynomial. I'd like to know a deeper relationship between virtual genus and the index polynomials, but I don't know it at this stage. So that's where I stand at the moment with the index polynomial, and I see that we have a little more time. So let me just go back and talk for a few minutes about the elements of Carvanothomology, just for a few minutes, and then we'll stop for today. So going back to Carvanothomology, going back means actually going all the way back to the bracket and thinking about it again. And I'm going to first do it just for classical knots, and then we'll understand how to add virtuality. So here's the bracket again. And then here is the way to think about the states of the bracket. So I can think of the states of the bracket polynomial by thinking of all the A smoothings first. And then one step at a time, I can change one A smoothing at a time to a B smoothing, and I get a second line. And then I can change another A smoothing to a B smoothing, and I got a third line. And then in the case of this trefoil, my fourth line is the end, all B. But you can always do this. You can start with all the A's and then take arrows that point from n A's to n minus 1 A's and 1 B, and then arrows that point from a situation with 1 B to a situation with 2, situation of 2 to 3, and so on. And you will find that what you have drawn is a cube in the process. And this cube is a pattern which is going to lead us to defining this homology theory. The pattern of the cube lets us should be thought of as a category, or can be thought of as a category, where each arrow is an arrow in the category, and the objects in this category are the states. And then, of course, you have more complex morphisms in the category, like going down vertically and then off to the left here and then down there, compositions of these arrows. And so this is actually a finite category in the sense that there are no infinite compositions of arrows because they all go from one vertex of the cube eventually down to the other vertex of the cube. And of course, if you're going to think of it as a category, then every object has an identity morphism as well. Now, it turns out to be useful, and this is worth introducing now so you might get used to it. It turns out to be useful in keeping track of the bookkeeping for what we're about to do, to change the variables in the bracket a little bit. This variable change makes the value of the loop equal to q plus q inverse, no negative sign there. And I put a minus q on the b smoothing and a 1 on the a smoothing. And that's my new version of the bracket. You can think of doing that by multiplying by power of a, the usual bracket, and replacing the a by minus q inverse. But you could just take it for what it is. There it is. And then if you have an extra loop, you multiply by q plus q inverse. Now you may want to see how is this related to getting an invariant polynomial since we changed these variables. And I'm just checking to see if I put that in a place where it's easily. So this is a good place. This is actually a good place to do a little exercise, and then we'll probably stop. Let's figure out how this behaves under Randomizer moves if you had written it this way. So we're going to play with a bracket which is now defined like this. A smoothing gets a 1 minus q on the b smoothing. And the value of the loop is equal to q plus q inverse. So then let's see what will happen. Suppose that I have a little curl here. Then this is going to go to that minus q times that, right? Yep. So that's going to be equal to q plus q inverse minus q times this, which is just equal to q inverse times this. And what happens if you add it the other way around, like that? Then you would have the A smoothing would be like that, and the B smoothing would be the other way. And so now we would have 1 minus q times q plus q inverse multiplied by that, which is equal to minus q squared times this. Bit strange, huh? And here's what you're going to find out. You're going to find out that the way to normalize this is to take minus 1 to the number of minus crossings times q to the number of plus crossings minus 2 times the number of minus crossings times this bracket. Now, I think you're going to be able to see, if I remembered this correctly, that this is now invariant under Randomizer 1 moves. Let's check. This is a positive crossing, right? And this one here, this is a negative crossing. So, positive crossing, that would give you a 1. No negative crossings coming from this. That's a 0, that's a 0. So you would be multiplying by q to the 1, and that would cancel out the q inverse behavior. Try this one. Here, you have a negative crossing, so you would have minus here, and there's no positive crossing in the local thing, and you would be multiplying by q to the minus 2, but it got multiplied by q to the 2 and a minus, so that also canceled it out. Great, it works, okay? So it turns out this is it. This is the normalized invariant. So we can call this the Jones polynomial. And in fact, it is. You could use T and call it the Jones polynomial in the usual way. So while this looks a little awkward if you're thinking in terms of the usual bracket thing, it normalizes quite naturally into something that's invariant. But we haven't finished our exercise. Let's finish our exercise. How does the bracket behave under a second Randomizer move? Well, let's see. According to my work, this is going to be this minus q times that. And now I've already forgotten, so maybe I should just go ahead and do it again. This is going to be equal to having an a this way, which will give me a 1. Give me a 1. Minus a q times a loop. Then we'll get a minus q, and we'll get a 1 minus a q times this. Yeah. So we get this, then we get minus q times q plus q inverse times that, minus q times this, plus q squared times this. And if life works out well, there's the plus minus q squared plus q squared, minus 1 plus 1, all canceled, and we got minus q times this. And of course, one of these is plus and the other is minus, and you can check that that this gives invariance when we take the normalized formula. I leave it to you to check. Minus 1 to the n minus, q to the n plus, minus 2n minus, times bracket normalizes it. And what about the third Randomizer move? Let's just move in over here in the corner and check what happens there. It's the old story in that case. We have this, and this is going to be expanded into that. But now you have a Randomizer 2 move, and when you pull it out, it multiplies by a minus q. And when you put it back in, it multiplies by a minus q inverse. So after you pull it back and put it back in and get it down there, nothing has happened at all. minus q times the other guy. And then this is just exactly what happens if you expanded it below the line, at the line below. And so it's invariant under the third randomizer move, and it has a little odd shifting change under the second randomizer move. And that's what happens to this new bracket under randomizer moves. And now I just need to tell you one last thing that is fun, which is this, that what we can do is we can label the loops by plus or minus 1. And then instead of thinking of this loop as having q plus q inverse as its value, you can think of it as being the sum of the loops labeled plus q and the loop labeled minus 1. And then all this works out for multiple loops. Every loop, every pair of loops will give a pair of loops gives 4 of these labeled states, and you add up the values and you'll get the q plus q inverse squared as you should, and so on. So we can use these enhanced states in this way, and we can write the bracket as a sum of monomials. So the bracket ends up being written as a sum of monomials this way, powers of q, with some indices that have to do with how the states are labeled. And then from there, we can start working our way towards how this is related to, how this generalizes to a homology theory. I'll be putting this slideshow with its introduction to Carvanothomology into the Dropbox after we've talked, and you can use it and a paper that I'll include that's a survey about Carvanothomology to start this work if you haven't studied it before. And next week we will continue from about this point talking about Carvanothomology. That's it for today. Are there questions? Okay. If it occurs to you to ask some questions, I'm always available by email during the week, and we'll see how this goes. Thank you for listening, and I'll see you next week.
Thank you.
Good night.
Good night.